brief overview of Adams Realtime, and then really we'll get into the real focal point of Tony Gee's presentation, and then more from us on how to leverage Adams Realtime later on. So for what I'm going to cover, it's just briefly look at why we actually developed Adams Realtime, look at where it fits in the market, how it works at a very high level overview, and we'll talk about some of the applications, the benefits, and then where are we heading with this to as far as future development. So, everyone knows that Adams is the premier tool for multi-body dynamics across many different applications, from the vehicle dynamics for ride and handling to safety and durability. But we've received over the years lots of requests to leverage Adams in different application areas, such as hardware in the loop test benches, driving simulators, and in the ADAS and autonomous areas. And so to cater to that, back in I think 2017, I think was when we first developed Adams Realtime. We did that to enable us to take the Adams technology and to make it available in these applications. As far as where it fits in, there's obviously lots of different solutions out there that have been leveraged in these areas. If we look at the image I have on the screen and look at the high-speed areas, such as for analytical models, gaming engines, and reduced order models, they've been utilized because they're fast, but they also have some simplifications in regards to the accuracy level of the models. Reduced order models typically are done by taking characteristics of the suspension systems and converting those to lookup tables. And so that you have these nonlinear representations connecting the wheels to the body of the vehicle. And that's how you can get those sort of high speeds. Whereas at the other end, obviously, we have traditional MBD type models, and then even more complexity when we add things like flex bodies, which give you very accurate representations, but obviously the run times are a lot slower. So, Adams Realtime really comes in to sort of bridge that gap. It's leveraging our Adams engine and making it perform at real-time speeds. One of the things I think is important is that with Adams Realtime, we still have the model topology we have in our full fidelity models, which can give us a lot of key result characteristics. What we're seeing is people are looking for higher results fidelity, and typically that means at higher frequencies. And so by incorporating or preserving the topology of the models, we're able to deliver a higher frequency response characteristics in the results. So how does that work? Well, it is still the same Adams solver. We just changed the priority on how it's iterating to focus on outputting time steps at fixed intervals. And so obviously this is a compromise where we're sacrificing a little bit on how many predictor corrector iterations we do in the intermediate steps to ensure that we're giving an output at the appropriate time delta. So one of the things that means is that we're not necessarily guaranteeing every model will run at real time in Adams, but it will do its best. So what we do is we focus on establishing areas where we can simplify the models that are not going to impact the results or the characteristics that are of our focus. So we can look at simplifying things such as flex bodies, anti-roll bars, and so on, to more faster representations, or taking an F tire, for example, and representing it as a Pachinko tire. But as I mentioned, because we preserve the topology of the system, that means we've got the suspension systems, we've got all the bushings, the springs, and so on. Those are still available parametrically in the Adams Realtime model. So we can go and easily modify a spring stiffness or adjust a hard point location and just simply rerun the real-time solver to see the change. Now, that's a big difference to the reduced order models, which have to go through typically a calibration conversion process where they'll take a high-end model, or in some cases KNC data, and go through a series of articulations of the model to capture those characteristics in these lookup curves. But anytime you change the topology, so change a hard point, then you have to go through that entire process again. With Adams Realtime, we don't have to do that. In terms of the application areas, when we're talking about hardware in the loop, again, what we're focusing on here is being able to vet the performance of subsystems, and whether it's ABS systems, steering, power transmission, etc., by hooking it up to a virtual vehicle. And obviously, if you're in the industry, then you understand the challenges you face in getting access to prototypes earlier and earlier in the development cycles. It's getting harder and harder. And so it's beneficial to have a virtual representation of that vehicle that you can test your subsystem in the context of, so that you can vet the performance in a more realistic environment than just on a fixed test bench. And so that's where, obviously with the Adams model and the higher fidelity result characteristics, we can offer a more accurate solution for the response of the vehicle to the subsystem and the vehicle states that we're passing back to that subsystem. Similarly, with simulators, it's the same sort of thing where, again, we're capturing the inputs from the driver, applying those to our vehicle model and to the road conditions, and then giving the vehicle response to then be articulated through the simulator. But again, here the goal that we see and the trends that we're seeing is that simulators are becoming more of a front-end tool in development because of the lack of physical prototypes and the costs. So that they want to be able to test their virtual vehicles and really get a feel for what are the ride and comfort characteristics and the vehicle dynamic performance early on. And so that means making sure that we've got good, accurate models that we can run at real time to deliver that extra level of feel that they're trying to get back to really fine tune the vehicle ahead of production. And again, it's a sort of similar story with ADAS and autonomous. What we're talking about here is being able to test either virtual or physical sensor systems in a virtual environment that accurately represents the real world, so that we can really go through and test and verify the performance of these under all sorts of different conditions. That's, again, obviously with the complexity in vehicles getting more and more challenging, this is critical to be able to test the permutations and combinations of sensors, weather, vehicles, different events, and so on. So again, here we've got the ability to leverage our Adams model either in real time or in offline to really go through and test the corner cases, which are really more the important ones. And it's valuable because when we start looking at these different safety systems and what they're doing, we need to make sure that they're the way that we're assuming that they are behaving or being affected by the vehicle are accurate. So, for example, maybe the bracket mounting system for a sensor has some compliance, or it gets excited under certain frequencies. So we need to be able to test that system to make sure that that compliance is not adversely affecting the performance of the sensor. Or in extreme braking conditions or cornering conditions, that the orientation of the sensor is not making it unable to detect what it's been meant to be looking for in the environment. So again, that's where having a good representation of the vehicle to give that response is very critical. This is just a couple of examples, and I apologize if the animations are a little jittery over the broadcast. But in the top, we're comparing more of the simple four wheels and a body type representation going over some speed humps versus the Adams representation, where you can see with that extra fidelity in the Adams model, we really do feel the impacts of going over those bumps on the vehicle, or in a braking situation on a slippery road. Then on the right, we're just sort of showcasing here again that we can really take this to quite levels of complex vehicles. So in this case, a truck where you've got compliance between the cabin and the chassis that can come into play with, again, the articulation of the sensors during different maneuvers. So just to wrap that up in terms of the key benefits, again, probably the number one thing that we're focused on is having a single source model that can be leveraged for both real-time and non-real-time applications. So from that one model, we can pick and choose the representation that's appropriate for what we need to test and validate. And by doing that, we're eliminating that challenge of having to go through translations or calibration processes every time we do a design change or want to adjust something to explore the performance, which again makes it a lot easier for us to leverage our models to tune and optimize them efficiently. And again, that you'll see a bit more of that later on in the workshop. And as I mentioned, it's the parametrics. So we have full access to the parametrics in our models and to be able to interact with those for our real-time workflows. So as far as where we're heading with this technology, something that we continue to focus on is obviously focusing on performance of the solver itself. And we've made quite significant inroads into increasing the solver performance over the last 3 to 4 years. And so we'll continue to make emphasis to do that and also to improve performance with multi-threading and so on. The other area is to look at areas where we can help in simplifying advanced models, whether they're leaf springs and bushings, and provide tools that can automatically simplify those down to faster solving representations, which still give a good results representation as well. And then the third point we're focusing on is looking at ways we can automate this process. So identify key performance characteristics for certain events that you want to be preserved in the real-time model, but then let it go through and automatically iterate through varying different ways of simplifying the model complexity to achieve those performance goals, but deliver a real-time performance. Those are the three key areas that are part of our focus moving forward in the Adams team to deliver those to make this whole ability to leverage Adams for real time a lot easier and more of a turnkey solution. So that was what I wanted to cover. So I'll pass it back to Hamath.